Okay, so this is lecture 11 of our semester. So, lecture 11. We are currently working with two-dimensional or three-dimensional. Okay, let me get started once again. Okay, welcome to the lecture 11 of our computational microelectronics course. And currently we are working with two-dimensional or three-dimensional structure. So in the previous lecture, lecture 10, we have thought about how can we represent our structures with a certain structure file format. So at that time I proposed to use two different files which contains information about vertices, and another one is another file for containing information about elements. In this case, vertex is just one-dimensional quantity, so in every case it is just vertices. However, in the case of elements, if we are considering three-dimensional case, then we have to specify 4 points to represent each tetrahedron. And if we have 2D case, then we are allowed to specify only 3 components to specify vertices of a triangle. So I hope that now you can draw arbitrary structure specified by these two files. So now we are ready to calculate certain equations defined on that domain. So that is the main topic of today's lecture, lecture 11. Although we will consider very simple equation, the Laplace equation, but in my opinion, if we can do it for the Laplace equation, actually the equations we are considering in this computational microelectronics does not deviate much from the Laplace equation. So I think that this is sufficient for our purpose. Okay, so now let's go to the Laplace equation in 2D or 3D equation, 3D domain. Before talking about the 2D or 3D case, first revisit the discretization in 1D case. If we consider the Laplacian of a certain unknown variable phi, then in 1D it can be just written as just the second derivative of our variable with respect to the only spatial coordinate x. Of course, if we expand it to 2D or 3D, then we will have certain component corresponding to the second derivative with respect to y, or second derivative with respect to the z. But in the case of 1D, it becomes just second derivative with respect to x. So now we know that if we have a non-uniform spacing of delta x, then at a certain position x sub I, here I is an index, integer index to represent our position, then it can be written as this form. So now I think that you can understand this form quite clearly. For example, let's do it. It can be regarded as this one, can be regarded as this way. So if we take the partial finite difference of this one, so this is derivative of the first derivative. So we can say that it can be written as a form like this. So first derivative calculated at a certain point, and another first derivative evaluated at a different position, and their difference is considered here, and here happen to be, we can say this is half a point and this is half a point. So simply speaking, let me just draw a diagram here. Let's say that this is a delta x and this is a delta x sub I, and it is x sub I minus 1, and this is xi plus 1. Then we are now doing this job. Evaluate the first derivative at this point and evaluate another first derivative at this point and take the difference. So since every spacing is written as delta x, still we will have delta x. So taking these two different values and normalize it by delta x, and of course if we take certain limit of delta x approaches to 0, then that will become the real second order derivative. However, we have some approximations here. One is our delta x cannot be an infinitely small value. So this is finite difference. Finite value. And also here we define the first derivative at a middle point and another middle point. However, unfortunately, even this first derivative cannot be calculated accurately, so only in an approximate way. So therefore, our expression for our second order derivative cannot be exact in an analytic sense, but we will just live with this approximated form. So if we understand our limitation about this discretization procedure, then it is completely okay to understand this kind of expression. So we just try to estimate first derivatives at these 2 points and takes the finite difference of them. Yes, now we can do it, and let me just explicitly show it here. Then how can we evaluate the first derivative evaluated at a midpoint between xi and xi plus 1? How can we calculate the first derivative? It is done quite easily by taking the position difference and taking the values at here and values at here. So we will take the difference of phi at x I plus 1 minus phi at x I. Once again, if we take this limit, then of course it will approach to the real, the actual first order derivative, but our delta x cannot be infinitesimally small, but we will say that okay, this is a good enough expression for our first order derivative. So now if we adopt a simplified notation for this phi at xi plus 1 as phi I plus 1, and this one phi evaluated at x sub I just like a phi I, then we can write down in this manner. So if we rewrite this term as delta x here, phi I plus 1 minus phi I. Yes, that's it. And we have a minus sign here, and we can repeat this job once again for another midpoint between xi and xi minus 1. So it can be written as this form. Yes, so not that difficult, and when we just combine them all, then we will have square of delta x in this low part, and here we have I plus 1 minus 2 times phi I plus phi I minus 1. That will be the expression shown here, and you know that this is valid for the uniform spacing of delta x. Now I think that you have already applied this kind of approach to your Poisson equation. Then when you solve the nonlinear Poisson equation in substrate, you have already done it. So I hope that you are quite much familiar with this kind of discretization approach. Then let me just justify or generalize this approach with a little bit more generalized case of non-uniform spacing. Up to now, I have assumed that every point or every pair of 2 points, neighboring points, is given as just delta x. If we have x sub I, and if we add delta x once, then that will become yes. So if we have twice of delta x, then we will have xi plus 2. So this kind of assumption was used in our previous treatment. However, in reality, our spacing can be quite non-uniform, even if we consider structured grid considered in our previous lecture, lecture 10. It can be a non-uniform one. For example, let me just show it once again with you. So if we visit our previous lecture material, lecture 10, and at the time we have thought about a structured mesh, and this is a typical example of a structured mesh, and x directions and y direction we have directional meshes, and each lattice point is corresponding to our two-dimensional mesh point. When you have a look at this x directional mesh, you can immediately find that okay, here we have point, point, and point, point, point. So in this case, we cannot say that these points are distributed with uniform spacing. So in general, we cannot assume uniform delta x spacing. Then how can we generalize our previous approach to this non-uniform case? So let me just do it together with you. So that is done by integration over a certain range, and that range is given as this and this from the midpoint between two neighboring points. So although we have to calculate the value at a position x sub I, but instead of calculating exactly at that point, we want to make a certain average over small domain or relatively short domain. The domain is given as xi minus half, xi positive half plus half, and here we can make it this way. If we have a certain quantity f which should be defined at x sub I, then instead of immediately calculate it, but we wanted to this job, integrate over our lower limit to upper limit, and also calculate this integral from a to b. Of course, here a is lower limit of our integral, and b is upper limit of our integral. If we do it properly, then we believe that although this is the value assigned at x sub I, but it is approximated as an average value, but not all over our entire domain, but domain which is highly localized only around x sub I. What is the importance of this one? Previously, if we don't have this f value exactly defined at x sub I, then we were not able to calculate this value immediately. But if we allow this kind of short interval integration, then at least we can try to find out a certain form of f over our integral domain or integral range, and within that range, using different informations, for example, the quantity defined on midpoint, then we can reconstruct the function. So let me just come back to this case once again. So if we are asked to calculate the second derivative of our quantity at here, then it is very difficult for us to calculate it immediately. However, by allowing the integration over this range, so this is corresponding to one midpoint and the other midpoint, then now we can understand this kind of integral can be reformulated to the other one, and other quantities can be also approximated. Let me just do it here more clearly. Following these approaches, so the node value is just approximated as a certain integral or averaged value. So now we can have this length of our integral. So this is upper and lower point, and their difference just corresponding to this lower part. And now we have an upper part corresponding to our function integrated over our integral domain, short domain. Point is, since it has the form of derivative, integral can be evaluated analytically. So since this is just integral or derivative of a certain quantity, the required one is just a difference between the function evaluated at upper point and the same function evaluated at lower point. So now you can do it quite easily. So then, how can we actually evaluate this one once again? So now we need the first derivative evaluated at midpoint once again, but there is no limitation about uniform spacing. In this case, we can just once again approximate our first derivative at midpoint with this finite difference, and also this is an approximated form of d phi over dx evaluated at another midpoint corresponding to a lower limit. So yes, this is just for integrated Laplacian operator in the 1D space. So simply speaking, if we have to consider Laplace equation, which is corresponding to the second derivative of our unknown variable should vanish, and in its integrated form over short range, it can be written as this form. So please note that this is not the unit or dimension of a Laplace equation itself. If we are really working with the Laplace equation, then it should have a dimension of phi function twice derived against this x variable. So if phi has a unit of, for example, voltage, and if x is meter scale, then our quantity should have a dimension of voltage per square meter. However, when you have a look at this equation, can you see the square meter in lower part? Actually not. You can see that phi, yes, phi is corresponding to the volt quantity, and here you have just x. So its unit is no longer volt per square meter but volt per meter. Why do we have this unit difference or dimension difference? It is because the operator we are currently writing down in this page is not actually corresponding to second order derivative, but we are now just writing the integrated version of our second order derivative. So that's the reason why we have just first order derivative terms here as two terms in the left hand side. Okay, so simply speaking, the general trick which can be used in this 1D case is just to integrate your equation of interest within short range around the discretized point, mesh point x sub I. Then you will have a quantity or an equation corresponding to the integrated form of your equation. In the case of Laplace equation, that will be the form, and you can easily expect that if every points are uniformly spaced, then that will become just the same form. Let's say that this is corresponding to the delta x, and this is corresponding to delta x. In a case of a uniform case, then you will have delta x, they share the same part, and now you can write down in this way. Yes, this becomes the integrated Laplace equation. So please make a comparison between this form and the form shown in our previous slide. Here, the form shown here. What is the difference? Here we have second square of delta x, because we are now talking about the discretized form of the Laplacian operator itself, and in this case we have integrated once over short range whose length scale is just delta x. So that delta x once gone, that's the reason why that 2 now becomes just first order here. Okay, so now this is the form for our Laplace equation even in a non-uniform mesh. So now you can solve this Laplace equation in 1D case without a restriction of uniform spacing. So please do your calculation. So of course this example just showing the solution for uniform mesh. For example, here and here and here we have the same distances, so it's not that interesting, but if you are interested, please introduce a non-uniformly distributed mesh and please try to solve this one. Of course, before wrapping up the first part of our lecture, I want to say that we need the boundary condition, of course. So up to now we have thought about the discretization of Laplace equation itself. However, in order to get the specific solution, we need supplementary boundary condition. So in this case, if we are considering 1D case, what is the boundary? Boundary is corresponding to the leftmost and rightmost points, and we must specify the values at these 2 points. So this is corresponding to the, for example, in this case, we have specified that, okay, this is 0 at position 0, and this is corresponding to phi equal to 1 at position, another position, for example, 5 nanometer. So without specifying these 2 values, so you cannot have the solution. So please be careful to solve this equation. Okay. So it was the discussion about 1D Laplace equation. What we have done is just to reinterpret the same thing with a slightly different trick. So we have introduced integration of our equation of a short range, and it worked, and we were able to get working discretized form. So now we wanted to expand our approach, the same approach, to 2D or 3D case. Once you understand that philosophy, then it is not that difficult to extend it to 2D or 3D case. The main point is the thing we wanted to calculate is not exactly the equation itself, but the equation integrated over a highly localized domain, small domain. Okay, so then in order to make it clear, so let me just spend 2 more slides on some stuffs. Okay, the first one is divergence theorem here. It is simply stating this one. So if you already understand the divergence theorem, then I will be very happy. But let me just repeat this stuff once again for some guys who are not that much familiar with this concept. So let's say that this F is a vector field. So this is position dependent quantity, and it is vector, and we must take divergence of this vector field and integrate it over a certain domain omega. What is omega? So it's up to you. So you can just think of a certain volume, and yes, this is the volume integral. And consider another one, surface integral over its surface. For example, let's say that this small box is corresponding to, for example, omega. Then what is its surface? Its surface can be identified as a set of 6 surfaces was shown here and there. You can imagine a set of 6 small rectangles, and that will be corresponding to this round omega. Okay, once you understand this one, on that surface, on that closed surface, you can also consider the integration of this quantity. So of course f itself is a vector quantity, so it can, let's say this is the sorry, I think that maybe we need different color for better visibility. So let's say that this is the surface. So here we have a certain point. Then even at this point called as R, our vector field F can have directional component. For example, this can be a vector f. So if we just integrate, then it will give us still a vector quantity. However, we wanted to project it to a certain direction. Then what is the selection of direction in our case? For that purpose, we introduce out normal direction n. So on a point in the surface plane, we takes our normal unit vector n, and by taking the inner product between f function and this n unit normal direction, we just project our f function to this normal direction. So simply speaking, what is it is, since n is unit vector, so it does not change its magnitude, and just taking this inner product gives us a normal component of f is taken. Then this normal component of vector field f is integrated over our surface area around omega, and divergence theorem states that these two quantities, left hand side volume integral and right hand side the surface integral, they are identical. So that is divergence theorem. This divergence theorem is repeatedly used in many cases in our computational microelectronics, so we must get familiar with this one. Today we will immediately use this divergence theorem to extend our Laplace equation for 2D or 3D case. And another one is, we have to have a clear view about our mesh structure. Although we can extend it to the even three-dimensional case, for your simplicity, I will just talk about 2D case. So please have a look at one typical example. Well, we can have many different numbers or points. Previously, if we adopt just how can I say, the structured mesh, then the way we specify R, a certain point would be I, J, K. We will need 2 or 3 integer numbers to specify directional component. For example, 3,4, 5,7. That will give us a certain point. However, in this unstructured mesh, we have no idea about what is 3,4 or 5,7. So instead of that, we need a single index. For example, let's say that this is index 5, 6, 7, 8, 9, 10, 11. Well, is this the golden rule for labeling those points? Absolutely not. This is just an arbitrary choice to label them all. So it means that our numbers, index numbers, are completely arbitrary. Once you have the 0.5, but can you expect that number 6 is just nearby, or do you have any guarantee that number 100, index number 100 is far away from you? So it is not guaranteed. Actually, these indexes are completely arbitrary, so you must consider general case. Well, anyway, let's assume that this is happen to be a certain point Ri, and of course it will have a surrounding points. Usually we consider the first nearest neighbor point. Well, for example, now we can consider this kind of realization. Well, say that sometimes we may have these kind of points. Then, for example, this point and this point is not directly sharing the same element, so this is not corresponding to the first nearest neighbor point of r sub I. But instead, well, if we go to once, twice, then we can meet this point, so this can be regarded as second nearest point in its connectivity. However, usually in our treatment, we don't care about this second nearest neighbor. We just consider first nearest neighbor, and we will consider a set of these ones, these points, and these points will be just collectively called as r sub j. So here j means that another index only runs over its nearest neighbor. Okay, so are you with me? I mean that if we have, for example, this kind of although this is quite regular, but this is practically quite important implementation. So let me just show you. So let's say that this point, the center point is your r sub I. Then please run over your r sub j. What is the relevant, the first nearest neighbor of this r sub I? In this case, you have to find out, run over this point and this point and this point, this point and this point and this point. This is a little bit counterintuitive, because when you talk about the nearest neighbor, if we just follow the distance, then you can easily understand, okay, this is upper point and lower point and right point and left point. So it is easily understood. But if we consider this one, although they are far away from compared with this, the real nearest neighbor, however, they are really connected to our center point r sub j within an element. So therefore, our nearest neighbor learning should be done also for these 2 points. So please understand, what we are talking about is the connectivity through an element. In the case of 2D, an element becomes a triangle, and in the case of 3D, it is a tetrahedron. Okay, so then now you can think about 2 different quantities. What is the two different quantities? First one is, let's say that this is happen to be our r sub j, realization of r sub j. Then what we can consider, of course we can define many different quantities, but practically we have 2 important quantities. One quantity is the distance between these 2 points. However, this distance is quite easy to calculate. What is the distance between these 2 points? Yes, distance itself just to calculate by taking the vector difference of r sub j and r sub I and taking the absolute value. It is easy to evaluate, and this is quite easily achievable for our calculation. But another one is the quantity normal to this edge. So we can consider an edge connecting r sub I and r sub j. And if we consider this edge, at the same time we can think about this distance, the distance or length of this lead segment. So if we consider, so please try to imagine your three-dimensional case. Now you have several points in your three-dimensional space. For example, for your simple understanding, I will just draw regularly placed points. Let's say that this is our R sub I, and now we have points along x direction, z direction, and y direction. Then, of course, if I ask you once again the distance between this point and this point, it is quite easy to calculate this distance. However, another point is, what is the area normal to this edge? Here we have a certain edge, and we can consider a certain normal plane, so which is perpendicular to this direction. And what is the area of this plane? So that can be also asked. So, well, then, since the visualization of 3D is quite tricky, so please do your imagination in your place. But let me just come back to our 2D case. Then how can we obtain this length? Who decide this length? Why I draw this lead box or a small domain lead in that way instead of this way? For example, you may ask me, is this unique or not? Why the domain assigned for Ri, typically called as omega sub I, is drawn in that way? For example, we may say that, okay, Ri has typically have quite a short area, so let's say that this is our omega I. Or why we specify, why don't we just specify, okay, for those points it has a heavy dominance, and yes, let's say that this is our omega I, and against this point or that point it has a relatively lower strength, so it has a relatively really short distance. Of course, you feel that this is not a fair way to discretize the domain, because here we have many points and we don't have any preference on each point. So let's say that relative strength of a certain point over other points, it doesn't make any sense. So what we wanted to prepare is just separation of those points with respect to the distance. Distance is fair to everybody. So say that if this point is more close to this point, Rj point, we believe that it is reasonable to assign this point to R sub j. And if we have a point here which is more close to R sub I, then it is reasonable to assign this point to R sub j. So simply speaking, our rule is distance oriented. If a point is most close to R sub I, and it should be assigned to R sub I. Yes. So, for example, here we have 3 students in our classroom, and if we consider, for example, any point here, then this point should be assigned to you or you or you. So the way is just to calculate the distance. then we will have three distances, and the shortest distance determines which point or which vertex point we should assign this another test point to that node. So simply speaking, this is distance based approach. So let me just follow this way. Then how can you find the distance or this way? Let's consider once again only 2 points, r sub I and r sub j. Then how can we determine whether this point is more closer to r sub I or more close to r sub j? It is amazingly simple. Just consider an edge connecting 2 points, and there we will have a midpoint between r sub I and r sub j. And if we consider a normal plane in 3D and normal line in 2D, then that will be the boundary between Rj closeness or Ri closeness. Any point below this boundary will be corresponding to Ri close boundary or point. Okay, so however, please note that this determination is only done between Ri and another Rj, but you know that we can have multiple Rj points. So in order to say that this point is certainly belonging to r sub I, then we must learn over every available Rj values. So if we have Rj values, then yes, we can calculate another line and another line in this 2D. Yes, we can generate many different lines, and the intersect of all kinds of this half plane that is corresponding to the shaded area here, that is corresponding to our domain. Any point in this domain is most close to r sub I. Any other mesh point has shorter distance than r sub I. Okay, so this is the way we calculate this omega sub I. Of course, it has its name, and this is Voronoi diagram. So please, Voronoi diagram. I mean that if we have a certain point, then we can identify this omega I, and some of these omega i's, omega I, omega j, blah blah blah. So entire domain can be decomposed into this sum of a set of polygons, and this is corresponding to the Voronoi diagram. Okay, so now the point is, as I told you before, when we talk about this 2D or 3D case, always we can consider a central point and neighboring point, the first neighboring point, and between this center point and first neighboring point, we can think about there are two important quantities. The first quantity was distance, and another quantity was area normal to that edge, or in this case length. However, it is length because this is only 2D. Please extend your imagination. If we consider three-dimensional structure, then we have to have area over a certain surface or certain face of a polygon. Okay, not polygon, polyhedron. Um, okay, so now we understand these two things. It is easy to calculate the distance, and it is relatively more difficult to calculate this this red dashed length, but we will assume that we can calculate this quantity, and this quantity is called as or written as a sub I j. What does it mean? Here I is our center point and j is its first nearest point, and the relevant area is written as a sub ij. Why it is once again area? We are in general talking about 3D case, so that's the reason why it is written as area. If we specifically consider just 2D case, then instead of this area, we should write down, for example, length between I point and j point, but we will not make such kind of specification. We will just unify the same notation for 2D and 3D case. So are you all with me about these two explanations? So up to now, I spent quite a long time about two different concepts in our discussion. The first one was divergence theorem. I hope that you have already exposed this concept in many times in your undergraduate course, because this is related with just so maybe freshman or sophomore level engineering mathematics. And if we go to more specifically 2D or 3D mesh, I just introduced the concept of a Voronoi diagram, and this one we will define the control. It is called as a control volume of a point R sub I, and calculation of this Voronoi diagram, it is really mathematically tricky, so I'm not an expert on that matter, but fortunately there are many other guys who have developed good enough libraries for us. So when we have a certain point, fixed points, then this Voronoi diagram can be calculated accurately. So we are quite lucky living in this 21st century. So now we have enough background to develop our own theory here. Now, just like 1D, we integrate our equation over a short or highly localized domain. So domain is shown here, omega sub I. Once again, this is a control volume of Ri. The point is, any point inside this omega sub I is most close to I sub I. So yes, so over this omega sub I, then just applying the divergence theorem. Let's do it. Divergence theorem need the form of divergence of a certain vector field. Then how can we identify this vector field? So please note that in our case we must calculate Laplacian, and Laplacian can be expressed as divergence of gradient. Okay, so this divergence term is treated as our vector field. So gradient of our unknown variable phi, that is regarded as our vector field. Then immediately now we can write down in this way: on the surface of our control volume, we must calculate the normal component of gradient of phi. That's it. So that is our calculation. And now we ask ourselves, what is this round phi I? So let me just come back to our previous 2D example, and please try to identify round phi I. Can you draw or can you point out what is round Ri? Oh, sorry, round omega I. Round omega I should be identified as this surface. This is the surface corresponding to, yes, round phi I. And it can be decomposed into, in our discretized form, we can consider there is one segment, another segment, segment. The number of segments is exactly corresponding to the number of neighboring points. If we have, for example, 1, 2, 3, 4, 5, 6, in this case we have 6 neighboring points, so then it will have at most 6 normal segments, because we have 6 edges connecting Ri and allowed the Rj's. So yes, so let's come back to our case here. Now it can be decomposed into many different small pieces once again. So these small pieces, how can we decompose it to small pieces? It is corresponding to also what is its J value. So now we introduce the ln over J, and here we need aerial integration, and that aerial integration is just approximated as multiplying that area. Okay, so please be careful. What we have to do is actually like this. Let's say that over this surface corresponding to round R sub round omega sub I, for example, let's say that it has this vector. It has this vector. At several different points, we have different vectors. Then what we have to do is actually taking only normal component. What is the normal component? Yes, this is normal component, and this is normal component, and this is normal component, and this and this and this will be normal components. And just integrating this position dependent normal components over our segments, that will be the exact meaning of this integration over one segment. However, instead of doing that calculation exactly, because that is far beyond our resolution, because we have the information only at here, only node points have information about phi, so we cannot make a fine resolution between this point and that point. This is beyond our capability. So what we wanted to do is, okay, this is far beyond, we will just consider this one. Since its area is A sub ij, and at least along this normal direction, we can make a finite difference approximation for our normal component. So by multiplying these two, we will approximate our equation. For example, here we must calculate the normal component of gradient of phi, but that is just approximated as like this: j minus phi I, which is divided by rj minus ri. When you evaluate this one, actually that does not necessarily equal to the normal component of gradient phi everywhere on this segment. As I drawn just before, it can have many different values over this segment. However, we will just say that, okay, the quantity along this edge is the representative one, so it can be regarded as a delegate for all distributed values. So now it can be well approximated as this form. So this is nothing but the edge-wise calculation. We have calculated a representative value between Ri and Rj and multiply the area of a normal surface and make a sum over our surfaces or our neighboring points. So that will be the discretized form of 2D or 3D. Of course, if you are exposed to this concept at the first time, then maybe it looks quite complicated, but don't be afraid too much, because if you just apply it to more simple cases like regularly placed our tensor mesh, then you can immediately find that this is not that difficult. For example, please try to apply our two-dimensional expression for this relatively simple structured case. Then you will find that this is not that difficult to understand, although it says that quite looks like complicated. Only difficult thing is, once again, this calculation of a sub ij. If we have Ri and Rj, then what is the area of a normal surface? That is important one. So you must prepare this quantity before you starting the calculation. So this is, here I summarized how can we calculate this one. How can you calculate a sub ij? As I told you before, distance itself is really easy to calculate. So the remaining task is calculation of a sub ij. So in 2D structure, for example, this point is corresponding to the circumcenter of this triangle. Please have a look at this yellow triangle, and this point is obtained by taking the normal line and normal line. This is obtained by a cross point of these two normal lines from midpoints. What is it? If you have any triangle, you have three sides, and from two sides you draw the normal line from their own midpoints, and eventually you will have a crossing point, and this point is always the circumcenter of this triangle. You know it. So simply speaking, this is circumcenter of this yellow triangle, And if we consider another, this green triangle, and this point is another circumcenter of another triangle, what you can do is just to run over your triangles, neighboring triangles, and find out the coordinate of your circumcenters and calculate the distance between two neighboring circumcenters, and that will be corresponding to the two-dimensional version of your A sub ij. Well, then how can we do it for 3D case? Then of course this concept is still valid. If we, even though we have how can I say tetrahedron, but still those points will be once again circumcenter. However, calculation of those points, the corners of our polyhedron is more difficult. So this is beyond our capability in this class. So, but when we consider just the 2D case, then it is relatively easy to calculate A sub ij. So please identify circumcenters of your triangles, and you can calculate the distance between them. So not that difficult, so you can do it. Okay, so now if we go to the Laplace equation in its integrated form. Why do we have integrated form? Because we have already integrated our Laplacian operator over a small domain called as omega I. So now we have this form. Although it looks quite complicated, but all kinds of difficulty is hidden here. Calculation of A sub ij, that is important. So when you have a certain structure or certain device structure, what you have to do is calculate this A sub ij component. Then by evaluating this Laplace equation all over your points, discretized points, you will get the discretized version of a Laplace equation. Of course, my final comment is, of course, we need boundary condition. So previously, in 1D, we have two boundaries. Then we must specify values and values. Then how about the case in our 2D case? Let's say that now we have this domain. Let's say that this is our omega domain. Then of course, if we specify every values over entire surface round phi, yes, you will have a certain term, certain solution. But usually what we do in the computational microelectronics is not fully specifying the values at boundaries. Instead of that, we introduce a concept of contact. So on those contact points, we have certain values of our phi value. Phi is something. Phi is something. Also phi is something on those contact points. And of course, we can identify non-contact points. For example, for these, also for these surfaces, we don't have predefined values. So this is not related with the Dirichlet boundary condition. In that case, just leave them alone. Do not perform anything on those points. Then it is automatically corresponding to the Neumann boundary condition. Why? So please consider this point. Let's say that this is your R sub I. And now you have surrounding points. Please place some surrounding points corresponding to your RJs. Then please just imagine what happens when you apply your divergence theorem to this surface case. Then you will find that actually your integration domain should just look like this. That will be your integration domain omega I. Then now you understand, by performing this job you can specify the component contributions from these segments connected to the another RJs can be accurately calculated. But we have one missing part. What is missing? This part is missing. If we have to really evaluate the integrated Laplacian, then we must consider also contribution from this boundary surface. However, if we do not do anything, it means that the flux or normal component of gradient of phi along this surface, the boundary surface, happen to be set as 0. Simply speaking, by doing anything, we are now saying that on boundary it is corresponding to 0. Phi's gradient, its normal component vanishes. What is it? This is nothing but homogeneous boundary, Neumann boundary condition. So usually homogeneous Neumann boundary condition is a typical boundary condition for non-contact boundaries in our application in many cases. So that's the reason why for other non-contact boundaries we don't have to do that. Then how can you apply this phi value? Let's come back to our contact points, Dirichlet boundary conditions. In that case, this boundary condition has priority over our previous Laplace equation. So for contact points, please do not apply this Laplace equation. Instead of that, you must specify the boundary condition. So then you will get the solution. So our homework is typically quite challenging today. So that's the reason why I postponed the announcement of this homework to lecture 11, not lecture 10, because if I give it as a lecture or homework 10, you have just 2 days to perform this one. But now we are on Thursday and you have 5 more days to perform homework number 11. The problem is quite simple. Please load your your example, BJT example. Then you will have a certain complicated shape like this. And please specify 2 different contexts on that BJT example. Where should be the contact points? It's up to you. So please select any arbitrary 2 surface contact. Means that please do not assign your contact in this bulk node. It's not allowed. But for example, yes, it can be your first contact and it can be your second contact, for example. It's up to you. And please assign 2 surface contacts and set one of them as phi equal to 1 and set one of them phi equal to 0. Then you will get the solution. Just draw it. And once you draw it, the next task is now swap the value. Now previously 1 is now switched to 0 and previously 1 is now switched to 0 is now switched to 1 and solve once again. then you will have two copies of a solution obtained from two different boundary conditions. The final task is just to make a sum of them. So yes, then that's it. So in your report you have to specify where are your two contacts, and show the first solution and second solution, and finally sum of these two solutions. So that is the homework number 11 for you, and you have 5 more days to perform that one, so please try to do it. Okay, do you have any question? No? Then I will wrap up today's lecture, and if you have any question when you perform this homework number 11, then please let me know, because this is related with your first implementation of a 2D. Maybe that will be a little bit challenging to you. So if you have any question, then please contact me through email, then I will try to answer your question as much as possible. Thank you.